And hello, everyone. Welcome to the Senior Project Symposium. This is the Tailsitter VTOL UAV for search and rescue of drowning victims, funded by Lockheed Martin and advised by Dr. Bandari. My name is Nicholas Matar, and I'm joined here by some of our other members of the project.
Hi, I'm Stephen Perzo.
And I'm William MacArthur.
And today we'll be going over a few things about the design and how the final design, and then some of the results of our testing and analysis. So starting off with the overview, we're going to start off with the objectives and applications of our vehicle, sort of the why we built this, then the concept of operation, which we use as the mission profile and how the UAV is going to perform its mission, the organization chart, the system level requirements, which guided our design, the technical approach to the design, some 3-view drawings, the power budget, structures, control surface sizing, sort of the layout of everything, and the payload drop design for the life preserver, some of the manufacturing we've done, and then finally with the data analysis and results, some of the results of our simulation and testing, and then what we're planning to do moving forward for the next year of the project. So starting off, some of the objectives of the design. One was to build a blended wing VTOL tailsitter UAV capable of performing autonomous missions. So it will be autonomous during the entirety of its mission. And then to perform its mission, it'll utilize a infrared camera to be able to detect the drowning victim submerged in the water. So we'll be able to relay that information back to some ground station and assist the emergency responders by autonomously dropping flotation devices to those drowning victims to give them more time for the responders to get there and rescue the victim. Some potential applications are to assistance to drowning victims, as mentioned before. It's a bit quicker than traditional methods of rescue, especially because of things like helicopters take a bit longer to start up, and they're manned vehicles, obviously. So they wouldn't be able to perform the mission as efficiently, and because humans are limited by their own eyesight, it might be harder for them to see potential drowning victims. Additionally, it will provide emergency responders with accurate GPS coordinates of a victim through the continued tracking and monitor potential threats at a much lower cost than a manned vehicle. So here's that concept of operations we were talking about. As you can see, we start with an area scan over the area we believe is the drowning victim area. Through that active scan, we try to detect a heat signature. If that heat signature returns as not a person, then we will continue scanning until we detect that drowning victim and drop them the life preserver. From there, we can relay the GPS location to the emergency responders or the ground control station, and they can dispatch some responders to go rescue the victim. Here's the organization chart of the project. As you can see, Stephen is the team lead for the entire project, who's been guiding the design and the rest of the project, assisted by his deputy, William. And for my role, I was the chief systems engineer, so I handled mostly the requirements of the project. And here are the system level requirements. These requirements guided our design of the project. Throughout the design, we had to adhere to these to make sure that we were performing as expected of the mission.
For the technical approach, we decided to design a blended wing tailsitter airframe for the required mission and validate the design using simulations and hand calculations, as well as using sill and hill simulations to validate software and hardware. Next slide. Here's the 3-view drawing of the aircraft. It is a wingspan of 1.7 meters, an aspect ratio of 3.14, a max gross takeoff mass of 4.5 kilograms, flight time of 15 minutes, and a max speed of 16 meters per second. A couple of key features are the large center body for storage of all these sensors. Here's a 3D wireframe. You can see the hardware layout. We have 2 motors mounted on the leading edge ahead of the CG. We have the Jetson Xavier in the center of the aircraft, 2 payload drop doors, 1 on port and 1 on starboard, and PX4 flight controller in the center. Here's the power budget analysis as well as the mission profile for a battery capacity of 7 amp hours, and with the 50% throttle during cruise, 100% throttle estimated during climb out and landing, we can get about 15 minutes of flight time. The mission profile will take off in a climb out transition for about 1 minute at 52 meters altitude above ground, cruise at a speed of 11 meters per second while it's scanning, and return during that time and land within 1 minute. Here's some of the structure design. This is the spar. It's a 2x2 by 3.3 foot composite sandwich structure of carbon fiber and EPS foam. It was averaged by the thicknesses of the root and tip cord. And with a 3G load, we have a set factor of safety of about 0.2. Here's some of the preliminary manufacturing that we've been doing. Metal templates have been cut out, and then a hot wire bow is drawn across a block of EPS foam to cut out different sections of the wing. Those foam sections are then glued together to create the entire aircraft.
Okay, so to make sure that everything can take off, land, and fly properly, we need to have proper elevon sizing. So we came up with more or less 3 designs. The first one only really works in level flight, while the other 2 of percent chord length and the rectangular cutouts both work, while the yellow, the percent chord length, has a slower transition, and the blue, just the rectangular cutout, has a faster transition. Next slide. Here we have all of our electronics. We have a PICSOC for the flight controller and the Xavier for our onboard processing, with a FLIR VU Pro for our camera. Next slide. So this is the general proof of concept for our payload drop system. We have 2 bays, each with a servo and a rod attaching to the other end. So they would open like conventional bay doors. Next slide. It's seen as this here in a small proof of concept. So now we're going to go on to the analysis and the results that we got from the simulations. So first up are the dynamic stability modes. We have the short period, the spiral, the roll, and the Dutch roll. All of them are stable, while some take a little longer to converge than the others. Next slide.
Simulation and testing. These are all the softwares we were looking at for using to test both the hardware and the software, as well as to double check our vehicle dynamics and performance. As you saw on the previous slide, XFlyer 5 was used to check our stability, and it can also check our aerodynamic performance as well as various other things. Some of the other programs we were looking at were ArduPilot, which comes with the Mission Planner, which is a user interface that runs from the Pixhawk autopilot and is used to both configure the Pixhawk and be able to test various things via the Mission Planner interface that'll allow us to test the software in a ideal environment. Some of the other things we were looking at were flight gear and Gazebo. The issue with Gazebo is it's a powerful 3D environment, but it must be run on Linux, which is typically a good environment for software-related development. And then the hardware components can be connected to the host computer to add hardware in the loop capabilities and be able to verify our calculations. So next, talking about software in the loop and hardware in the loop simulation, we use those for simulating developed algorithms vehicle motion, autonomous flight, and then using the data we gather from those simulations, we can tune the parameters and adjust the aircraft. And then hardware in the loop simulation can be used to detect the problems with the flight hardware, software, and mission that may not have been according to the things we calculated. And then the nice thing about some of these simulation tools is you can also use them to practice flying the vehicle manually, which one of our requirements is that we have to be able to control the vehicle manually during any portion of the mission for safety reasons. And then the added benefit of these simulations is that, especially during this pandemic, we're able to utilize them in place of flight testing for now. And then moving on to victim detection. So this is some of the testing we did with the camera. As you can see here, we have 3 different images, one at long range, so the UAV is flying far away at a distance, medium range where the UAV is flying somewhat closer, and short range where it's quite close to the water. And as you can see, it's able to identify persons with some level of confidence and that are somewhat submerged in the water. However, there are some issues with this image recognition. As you can see here, it doesn't detect, on the left here, it doesn't detect every person that's in the water. It only detects 2 of the 5. And it doesn't have a very high confidence score on these detections. And on the right here, we can see false positives where it misidentifies people. So these are some of the issues that come up with the image recognition. And to address those, there are various things we can do. For one, we can train the model, so continue to train it to better identify persons and better analyze how to determine that the person identified is actually drowning from those images. And then we can also use better FLIR camera and image stabilization to make the image detection better and collect more pictures of swimmers to expand the data set and make sure the computer has a wide range of things to pull from when it's trying to detect people. Some conclusions and then moving forward. As you can see through our design, the final design currently meets most of the design requirements and the mission as validated by analysis and testing. Some further testing will be needed though, and some further simulation will be needed to verify some of the other requirements. The vehicle manufacturing processes and further structural analysis will need to be worked on as the project continues into the next year with new members, where we'll be designing the ribs and the rest of the aircraft. We'll also need to have a small segment of the team dedicated to simulation, as we've found that it is harder for a person to be working on something and also do the simulation as it requires a special skill set. And finally, the transition from vertical takeoff to mission needs to be further analyzed via simulation or flight testing as the project continues next year. We're looking to mostly test via trial and error as it is difficult to model this transition in CFD and XFlyer. And that concludes the presentation. Now is the time for any of your questions, comments, and concerns.